Hello and warm welcome to everyone. Today is the 22nd lecture of the course on financial econometrics. Today basically we'll talking about the different approaches to time series modeling. Specifically we'll be talking about two basic methods, that is decomposition and smoothing. As we have discussed in the last lecture, that the purpose of the time series modeling is basically use the past information to decipher the underlying patterns of the series and also to predict about the future. When we say to decipher or to know or to examine the underlying pattern of the any time series, that means basically we wanted to know about the trend component of the series or the seasonality component of the series and the random component of the series. And for that basically we'll be using the past information of the particular series. Before that, let us quickly see that what is the problem basically we have in the time series and why we need it. So in the last class what we have discussed, in case of time series basically what we have, it will violate the assumption of classical linear regression model. Specifically the residuals are independent, because when the time series means that the data has been chronologically ordered. So in that case, the observations will be related to the previous observations, and therefore we have the problem of the autocorrelation. And once we have that, that means the value of f and t statistics are overestimated. That means the parameters are not reliable. Another critical characteristics of the time series what we have, that time the moments will be the time varying. That is, mean, variance, covariance will depend on the time. As time changes, the mean and variances will change, and basically this leads to the property of non-stationarity. And once we have the data or the series are non-stationarity, then for example using the classical linear regression model will be misleading. That is, in most of the cases there will be problem of spurious regression. Therefore necessitates us a unique set of tools and methods for analyzing the time series. So basically today we will talking about what are the different approaches we have for the time series modeling, and the two basic methods we will discuss in detail. So the time series, in case of the time series modeling, so there are the different approaches. So first is time domain versus frequency domain. So in case of time domain, where the future value as a function of past value, we assume that future values are the function of the past values. However, in the frequency domain, what we know is that time series can be represented as a function of time, but in the form of sines and cosines. So instead of discrete, we use the functional form sines and cosine. And basically, the Fourier transformation is the critical in this case. So we use basically Fourier transformation to convert the time series data into the sine and cosine function. Then we use the different models to analyze this. So here we have the option to either choose the time domain or the frequency domain. Similarly, we can have the approach of univariate or multivariate. In case of univariate models, basically we use the single time series to build the model to analyze the different series. For example, autoregressive model, moving average model, or autoregressive moving average model, or the another variant of this ARIMA, which we will be discussing in details in the coming lectures, are the examples of univariate models. However, in case of multivariate models, where the two time series, maybe we will be using that more than one time series data, or more than one time series variable. So in that case, basically it becomes multivariate models. For example, vector autoregression or the vector regression models or the configuration methods. All these models is basically are example of the multivariate models. So in the time series, we can choose the approach of either univariate modeling or the multivariate modeling. In this course, we will be discussing both univariate and multivariate case. Then another dimension of the time series modeling, we have linear or the nonlinear time series models. In case of linear time series models, where we assume that the current value of the series or the future value of the series linearly depends on the past values. So the functional form we define, it is a linear. For example, this AR, MA, ARMA, all these are the examples of linear models. On the other hand, the nonlinear time series model, where basically we assume that the functional relationship is not linear. And there may be different reasons to have the nonlinearity in the relationship. There will be the complex reasons of that. One reason could be the structural break. However, in the time series, a lot of the development has been recently to incorporate the nonlinearity due to the structural break. So, what is the nonlinear? Basically, we develop the special models to deal with the nonlinearities that could have been induced by the structural break or any other form. So, basically, in that case, nonlinear time series analysis focuses on the two aspects, that is identifying the presence and timing of the structural breaks or the nonlinearities in the series and modeling data behavior before, after and between the different breaks. So there are many examples of the nonlinear time series. So this could be again we can group into the nonlinear models built around the different nature and characteristics of the nonlinearity. For example, we may have the threshold autoregressive model and the Markov-Cauchy models or the Arch-Garch models. Threshold autoregressive models, what we assume that the behavior of the series changes when it crosses a certain benchmark, certain threshold value. So if we wanted to capture that kind of nonlinearity, we use the threshold autoregressive model. However, the Markov-Cauchy model, it says that the relationship changing depending on the different states of the economy, different states of the volatility. So when the whole environment is changing, then the relationship changes rather than did not change due to the threshold value of any one variable. Then Arch-Garch, basically it is to capture the nonlinearity into the nonlinearities arising due to the changing variance, or basically what we use these models to model the volatility or the time variance. So let's now move to the second part of this lecture, where basically we'll be discussing two basic approach or methods, two basic methods to analyze the time series data. So these are the very basic models. Later we will see these models. We'll keep on adding on these models to account the different complexity in the data. So the first model we'll discuss about the decomposition. So basically, what is the decomposition? Basically, decomposition are the different statistical techniques which we use or imply on the time series data to break out the different components which yesterday we have discussed, that is the trend, seasonality, cyclicality and the random component or the noise component. Basically we use this model, we use this technique on any series to decompose that series into the different components so that we can identify what is the trend, what is the seasonality, what is the cyclicality behavior on that particular series and what is the random. There are the different decomposition techniques we have. So broadly we can say the classical decomposition, which has been originated in the early 1920s. Then within the classical we have the two approaches, that is the additive or the multiplicative. Then we have STL decomposition, where basically this STL refers seasonal and trend decomposition using the LOES, where the LOES is basically locally weighted scatter plot smoothing method. So to estimate the trend and the seasonal components. So let us discuss one by one here. So when we say aditic decomposition, so basically here what we are assuming that these components of this time series are uh, combined using the uh, feature of addition. That is, this combines additively. That means this the whole series yt is the summation of the three component series: this trend, seasonality, and the randomness. Here basically both the seasonality and cyclicality we have tried to capture using this one term, that is the seasonality. So this method is mostly appropriate when your seasonal behavior or the trend behavior of the data over the years more or less remains the same. So relatively it remains constant over the time. Then this method we use. For example, let us take the data on the Nifty 50 and we use this decomposition method. Then how it looks like. What can see here, this is the original data we have, and we have decomposed the three components of this particular data, that is the trend and the seasonality and the noise or remainder, or what we call the random. So this is the basically random component, and this is the seasonal component, and this is the original data. So from there, what we can see here, this plot particularly shows the trend, seasonal, and residual component of the series separately here. And by doing this, we will be able to analyze the trend behavior, that is the long-term behavior or on an average behavior. And we can identify whether there is the seasonal effect or not on this. So let us see here the trend and this component. So this is the Nifty 50. So what we can see here, okay, yes, there is the seasonal effect. That means on the buying and selling, the seasons do have effect on the buying and selling. However, if we see the trend, what we can observe here, in 2016 there has been dip. On the other hand, here to 2000, after 2020, around 2021, it has been dip, and here we have dip. So we can say, yeah, quite a period we have a stable relation, a stable phenomena, 2016 to almost 2018, 19. And from this, we can analyze the different reasons which has affected this. So we can say here, for example, in the Indian economy, so here where the GST and other rules have came, so it may be hit by that. Or here, for example, the COVID effect maybe, and this is the post-COVID rise. Then here we can see the this taper tantrum thing came here in this case 2023. So this says the behavior of the overall what is happening, and this signal basically shows what is. Okay, yes, there is the seasonal effect on the buying and selling on this particular uh, trading on this particular stock. And this bars basically shows the relative importance of the different components on the data. So obviously here we can see the seasonal and the trend has quite a strong effect on the data rather than the error component or the noise. So this is the additive decomposition. Similarly, we have multiplicative decomposition, where basically we assume that component sometimes is combines multiplicatively, that is yt is equal to, where we assume that yt is equal to t trend multiplied seasonal multiplied by the random. So here this will be the most appropriate when the trend and the seasonality components increases or decreases over time. Let us repeat the same method on the Nifty. So here we can see again the same thing, that the trend and this is the original data, and here we have. So again the same kind of inference we can get from here. So here basically shows that how this seasonal and trend compositions scale proportionately as the time passes over the year. So as we move, how it scales up in this case. Then the third technique of decomposition is the STL decomposition, which basically here what we have, the seasonality of any data, not only quarterly or annually, it can be decomposed and it will be able to capture the seasonal effect of any data, whether it's weekly, whether it's monthly, whether it's quarterly, whether it's yearly. So seasonal component allowed to change over time. It is not assumed that it is constant. For example, in an additive case, we are assuming that more or less over the years the seasonal effect remains constant. However, here it has been allowed to change. Then this method is also robust to the outlier observations. However, this method is not able to capture, especially in the stock market, that is the trading effect and the calendar effect. For example, let us say here we are doing the STL decomposition of the same Nifty 50 index. Then what we can observe here, this thing. And one thing you can strictly see here, it shows the relative strength of the seasonality is more compared to the trend and other part. If we compare from the previous, the seasonality effect was little less compared, relatively it was less as uh, here it is showing. So because here the seasonality has been allowed to change over the years as time passes. So these are the so that means this decomposition method we can use to break the series into the different components, and using those components we can analyze the data, what is happening in that particular data. And then obviously once we know about the trend or the seasonal effect, we'll be able to predict better of that particular series. For example, if you know that in the seasonality there is the more trading in the particular season, so we can predict if that season is coming, that there will be more trading on that particular season. So those kind of prediction we could be done using the decomposition method. Then the next basic method used in the time series, that is smoothing. Basically, smoothing is the same. We do the for the same purpose, that is to identify underlying patterns of data. That is what is the trend, and then what is the seasonal effect and the cyclicality. All those things we do. There are the different types of smooth we can do. One is the moving average smoothing. The second is exponential smoothing. So what is the moving average? Again, the moving average smoothing, we have the two types. That is the simple moving average method, and the second is the weighted moving average method. So basically, in case of simple moving average method, what we do for a particular window, we average out the observations. So basically, by averaging out short-term fluctuations, we are removing from the data, so that the long-term trend and the seasonal effects remains there. So in case of smoothing, basically what we are doing, the short-term fluctuations we are taking out from the data, either by using the simple moving average or by using the weighted average. In the simple moving average method, where we assume every observation has the same weight, or what we can say that every observation has the same predictive power. However, in case of weighted moving average method, there we assume that different observations have different weight or the importance for the current observations. Usually what we assume, the recent data has more weight, more information compared to the distant past data. So to capture that, distant past data's effect on the current data decreases as time passes. To capture that, we assign the different weights. So let's take here the simple moving average. So here we can see that this is the original data we had, and here basically we took the simple moving average with the Nifty 50, and the window we have taken the 50-day. So we have taken the 50-day window to average out this fluctuation. So you can say that we were able to remove quite of the fluctuations in the original data. And from this data, in the red line, what we can say, yeah, over the years it is quite stable, as, except at certain places it has been fluctuating. So this kind of analysis, this kind of information we can get using this. Then the second is exponential smoothing. In a case of exponential smoothing, we have the three types. That is the simple exponential smoothing, Hall's linear trend model, and Hall's Winters seasonal model. So in case of simple exponential method, what basically, again we try to remove the noise, but we use the different method. Here basically is the rule or the principle of this simple exponential method is that more weights should be given to the recent data. So the weights are exponentially decreasing rather than an algebraic decrease. Or so here what we basically assume, the weights are basically exponentially decreasing. The recent data has more information, and that should be used to basically smoothing out the data, or to find out the trend and pattern of the underlying patterns of the data. So here, however, in case of simple exponential smoothing, the problem is that it does not include or does not take account the trend or the seasonality. So we can write the simple exponential smoothing like this. Here st plus 1 alpha yt plus 1 minus alpha st. Where this st plus 1 is basically the smoothed value at time t plus, so it has a time t plus 1. So basically what we can say, the smoothed value at time t is the forecast for the time t plus 1. So here yt is the actual observation at time t, alpha the smoothed constant where alpha lies between 0 to 1. Here this st is basically, it depends on the previous value. So we can write like this st is nothing but alpha yt minus 1 plus 1 minus alpha st minus 1. So that's the sequence we use here. So if the higher value is alpha, that means make the model more responsive to recent changes, whereas the lower values alpha smooth out the fluctuations, favoring the longer term trends. So from here we can get this conclusion here. So now if we use the exponential smoothing, so what we can observe here, this is the forecast. Here one thing has to be mentioned, that often this simple exponential smoothing is used for the forecasting, so rather than using to decipher the trend or the seasonal component here. So one of the forecasting method, we use the exponential smoothing. So here, but basically what we can see here, we have used the simple exponential smoothing to forecast this. Often the forecast will be very stable, and these bars basically show the standard errors of this method. Then another exponential mapping method is Hall's linear trend model. Basically, this extends the previous model or the basic simple exponential model to account for the linear trend. However, it does not account for the seasonality. So the model components, we can say that this is the level, LT is smoothed estimate of the current level, trend is the smoothed estimate of the trend. So we can write like this, okay, level, it should be estimated like this using this particular equation, and the trend should be using this, and if we combine these two, we basically get the forecast value yt hat t plus h is equal to lt plus ht, where lt is this, h and t is this h is basically the forecast horizon. So for how many, so if we write t plus 2, that means 2 horizon we have. So here the b is the smoothing constant for the trend, and alpha is the smoothing constant for the level, and obviously both these lies between 0 to 1. So let us see here in this case the same data for Nifty 50 we have used, and this we have the forecasted value here. Then another method is the Holt and Winter seasonal method. Basically it extends the previous model to further account for the seasonality. That means this model account for both linear trend and the seasonality present in the data. So the model components, we have the 3 component seasonal, and this 3 is given using this formula here. So the trend using this, this label uses this, and the seasonality uses this. Then the forecast could be used this here. So what we can say here is that we have this forecast. Now we can compare to the last 2 exponential methods. This is quite close to the following the pattern of the original data. So that was the multiplicative form, and this is the additive form. So in the whole winter seasonal method, we have both approaches, that is additive approach and the multiplicative approach. And compared to the last two methods, this wholes and winter seasonal method, which captures both presence of trend and season, do have better prediction compared to other. So in the next class, we'll be discussing about the different complex concept in the next class. So that's all. Today we have discussed the different. Today basically we have discussed the different approaches of the time series modeling and the two basic method for the time series modeling. In the next class we'll be talking about the concept of stationarity. Thank you all and see you tomorrow.